We were talking about verifying units for our equation here on the period of a spring in motion. So we can say that 2 does not have units. Pi also does not have units. So we're going to look for our units under our radical. So under the radical we have mass, which is in kilograms. And we have the spring constant, as we said, was newtons over meters. And so how does that give us our units? So we still have kilograms on the top. And we remember that a newton is a kilogram times a meter per second squared, and still over a meter. And so our meters are going to cancel, and our kilograms are going to cancel. And we have seconds squared under our radical still. And when we take the square root of that, we end up with seconds for our time, for the period of the motion, how long it takes to do that one motion. The other equation that we have that's similar to this, it talks about the motion of a pendulum. So basically a mass on a string swinging back and forth. And they changed the equation a little bit to give us the length of the string of the pendulum, and that's being acted on by the acceleration of gravity, which while we're on Earth is 9.81 meters per second squared. When it's somewhere else, it will, of course, be something different. But again, the units would be meters divided by meters per second squared. The meters cancel out, and we still have our seconds squared under the radical, giving us our seconds for the units for period. So we'll do a problem using those formulas when I get to the problem set video. I'm going to carry on talking about the formulas that we have. So sometimes when we're given formulas, we talk about compressing a spring, and they want to know how much work is done. So when we think about work, of course, we remember our units for work are joules, and joules are also our units for energy. And so we have our equations here that should look pretty familiar to us. We've spent a lot of time doing those in previous chapters. So we know that in any motion, the total energy of the motion is always, always, always going to be the kinetic energy plus the potential energy. And we also know that anytime there is no motion, and so in this instance, a spring has been compressed or stretched as far as it's going to stretch, or a pendulum is raised up to its highest position, that the total energy will all be potential because the kinetic energy is going to be zero. And so we also know the total energy is still equal to potential plus kinetic, but in this instance, our kinetic energy is zero. We also know that the total energy, when the mass is in motion and has reached its peak velocity, that all the total energy has then been converted to kinetic energy. There is no stored energy left. So our potential energy at that point is zero. And so all the total energy will equal the kinetic energy. So if we can solve for the total energy of a situation, and we can solve either for potential or kinetic, we can also then find the other, either potential or kinetic energy. But the total energy of a system is always going to be, say, if it was 100 joules, it would be 100 joules at the top of the motion, in the middle of the motion, at the bottom of the motion, at any point in the motion, because it's always going to be the kinetic plus the potential energy. It's really important to kind of understand that concept, and then we'll move forward with that. So in our periodic motion, we are adjusting some of our formulas a little bit. We're then saying that the potential energy of the system at any given point is equal to 1/2 the spring constant times the amount that we move it squared. So again, this is the change in the displacement of the mass. So before we talked about how it was moved from its equilibrium point, from where a spring likes to stand with no motion, and whether it's pulled to this point or whether it's compressed to a smaller point. That would be the change in that, the difference between its equilibrium point and where the motion is going to start. And so if there's no motion, we know that the potential energy would be equal to the total energy. And We also learned a slightly different formula for this, so we can say that the total energy at that peak displacement is 1/2 the spring constant times the amplitude squared. So what's the difference between the amplitude and the change in displacement? When we're talking about our spring, we have our equilibrium point where our spring is resting. And then if I wanted to then stretch it as far as I could, I would say that this is then the amplitude of the motion. So from its equilibrium point to as far as it goes is its amplitude. But suppose I wanted to know the energy at any given point in between here. I could then measure its change in displacement. So the amplitude can also be considered a change in displacement, but it's as far away from the equilibrium point as it goes in this motion. So then I could use the amplitude here. And so then hopefully you can see that if it's at my farthest point of displacement, the total energy will be equal to the potential energy. And so my x squared would be, or my delta x would be the same as my amplitude. So I hope that helps you understand how those two things are related. Fortunately, our kinetic energy formula is still the same, 1/2 mass times the velocity squared. So if I can find the total energy of the system and I can find the potential energy at any given point, I can then use my original formula to find the kinetic energy and then either find its mass or its velocity. And we'll work through one of those problems in the next video on the problem section. So I hope that that kind of helps you kind of understand how we're going to use energy in the system. When they talk about work, it's how much energy, how much total energy in the system that's being used. And then the same thing for the pendulum. We can then use that formula to find the length of the pendulum or the gravity if we're not on Earth. So the next video I will do some problems and hopefully make this a little more applicable and understanding. All right, see you then.